Hi, good afternoon, and welcome to this special webinar from Zimmer and Peacock, and it's really specifically for our colleagues at Swansea University. With that said, let me go forward. So I have some slides, but I also want to say just very quickly that not everything is all talk and slides this afternoon. I do have some hardware in front of me, so we'll be doing some demonstrations and some show and tells on various technologies from what we call IVD to wearable biosensors this afternoon. With that said, let me go forward now with the slides. But as I say, there will be technology that we will be discussing as well. So I will be talking about this IVD technology, and I'll also be talking about these wearables as well. At Swansea, it's fair to say there's actually quite a lot of work on microneedles. The new CISM facility has the capability of making semiconductor microneedles. The microneedles that I'll be discussing this afternoon are actually mostly polymer based, but just to say Swansea does have a strength in microneedle technology, and it also has quite a lot of research going on in biosensing. Now, I think the biosensing at Swansea is mostly around graphene or field of GFET, graphene field effect transistors, and it's also around electrochemical biosensors as well. So you do have the Welsh Print Centre at Swansea, so there is obviously a background in thick film printing, but you also have thick film printing. People like Professor Owen Guy do screen printing as well. With that said, I will be talking about screen printed electrodes as well, but most of what I'll be talking about this afternoon is in the context of Swansea. So something I'll be demonstrating in a short while is actually a new technology. Stack is a bit of a sort of strange term, I know, but I will be talking about a technology stack where we'll be talking about the control of a new instrument from Zimmer and Peacock, and I've got my phone here now, so I'll just talk about this. So I'm showing you my video, and then having sort of put some context, I'll be talking about this hardware, and I'll be talking about the Bluetooth connection with that hardware. I want to talk about what I actually am showing on the screen at the moment. So what I'm showing on the screen at the moment is that at ZP, we do want the teaching, the research, and the translation of research to be kind of as efficient as possible. So with that in mind, at ZP, we've been working on a cloud system called Julie for the, let's say, the last 10 years. And Julie is whenever ZP does an experiment or we do something, make a measurement on our technology stack, we always send the data to the cloud. So that said, I'm just kind of actually navigating the cloud even as I speak now. So with that said, I just want to bring this up really quickly, that I'll do some measurements this afternoon, but what you'll see when I do those measurements is, in fact, we'll make a measurement and the data will automatically go up to the cloud. So you'll hear me talk about cyclovoltammetry this afternoon. When I do a cyclovoltammetry experiment, understand that all that data goes to the cloud. And the way our cloud system technology works is that once upon a time, you would be left in what's, kind of technology readiness level number 3, which is you would be left in raw data, or just with raw data rather. But the way our cloud system works is we're actually able to send raw data immediately to the cloud. And when I say you send raw data to the cloud, this could be in a teaching lab, this could be in a research project, or this could be in a project that was actually trying to translate technology. So even though we're gathering raw data in the lab, because the technology is immediately cloud enabled, we're actually able to process the data using this cloud system, no coding required. We're able to process the data and turn it into meaningful numbers. So for example, here I've done a quick, you can see I've got raw signal. We've processed the raw signal. We've looked at what's called the peak height and we've turned it into a concentration. So I'll be coming back to this during the webinar today, but I just want to give some context that there will be a lot of talk on science and the science of electrochemistry, but I do want you to know that the gap between what would have been a TRL3, a laboratory experiment, and what can now be a commercial, or even something that you can give to a clinician like at Swansea, at Singleton or Morrison rather, has shortened. So I'll be using apps this afternoon, but those apps are actually talking to the cloud. And in the cloud, we're processing raw data and sending back to our smart devices numbers or concentrations. So we're able to go very quickly from raw data up to the cloud. Cloud converts the data, data comes back to the phone, and you've got a concentration. So suddenly this gap between what you would do in the lab and what you could otherwise give to, let's say, the real world, the NHS, for example, has just diminished quite considerably. So as part of that, now I will be talking about, techniques like amperometry, but if you look at if you could see my video stream at the moment, you can see here that it sort of says sense it all on my phone. What I'm going to do is I'm just going to scan the QR code that I'm sharing now. So I'll just scan it. Now my phone has just changed that it's now able to do amperometry. This phone is actually in Bluetooth connection with a potentiostat that I have on my desk, and I'll do a demonstration later on. But if I could sort of say, what I'm actually saying here is I'm able to do amperometry, I'm able to do open circuit potentiometry, and every time I scan a new QR code, it's repositioned what the app can do. And this app is in Bluetooth connection with a device that's on my desk, and I'll do you a quick demonstration of that later on. So this is saying, okay, so, I'll make it up, Professor Owen Guy, one of his students, wants to do a square wave voltammetry experiment. So how are we going to do that? So we'll scan through impedance spectroscopy is up here, by the way. So anyone who's doing immunoassays, obviously looking at proteins, etc., there's impedance spectroscopy for you. Linear sweep voltammetry, square wave voltammetry, cyclic voltammetry, and then square wave voltammetry I know is also used up there. So I'll just scan that. So there we are. Now I've got square wave voltammetry. So this app immediately now thinks, now I'm in square wave voltammetry mode, and it's in Bluetooth connection with this device. So if I run this now, it will run the device and I'll be able to do square wave voltammetry. Once upon a time, the kind of software that would otherwise drive research instruments was all very menu driven. Look up your methods, underneath that method there'll be some sub methods, and it was quite confusing, especially if you're trying to teach this kind of stuff in a teaching lab. And I'll talk about the teaching lab scenario in a little bit as well. Now, this sounds a little bit unusual, but I'm just saying to you, right, here are some QR codes. These QR codes are essentially programming an app on my phone. My phone is in Bluetooth connection with essentially a potentiostat. But this is a device that can go from teaching and research to actual final world applications. And let me sort of show you that. So I know this one will make you laugh, but if I scan my app now, I can now measure the capsaicin in chilies. How? Because the technique itself is cyclic voltammetry, but because we send the data to the cloud, we're able to convert the raw signal into capsaicin concentration. Let's do another one that's kind of pretty, let's do ginger. I won't do ginger, but let's do pH, for example. What's the most measured parameter in the world? It's probably chemical parameters, probably pH, nitrate, total antioxidative capacity, something that happens a fair amount at Swansea. Some of our colleagues are very interested in sort of doing continuous glucose monitoring. So this app now, I've just scanned the QR code for glucose. So it's really just running amperometry. But because we can send the amperometric data to the cloud, and as long as we know our calibration routine, we can actually turn the raw signal into a glucose concentration and then send a glucose concentration back to the phone. So suddenly, what holds most academic research and teaching at TRL3 is actually the conversion of raw signal into information. And this technology stack actually does that conversion really well. So you're not stuck in the world of amperometry or open circuit potentiometry or impedance spectroscopy or linear sweep voltammetry or cyclic voltammetry. You can do all those techniques, and this is a tool for teaching and for research, but it's also a tool for impact, because in fact, if you do square wave voltammetry, you're going to end up with a peak or a area under a curve. And as long as you've done your calibration, so you know what that peak or area under a curve means in terms of concentration, you can put that into our cloud system and it will say, okay, area under curve was X, X times calibration factor means this concentration. It will calculate that concentration and send it back to the device. And again, your gap between lab experiments at technology readiness level number 3, and something that's much more presentable to a real end user who's not going to be able to interpret your electrochemical signal, for example, is just significantly narrowed. So I will talk a little bit about microneedles this afternoon, because this is a technology at ZP that we're super excited about. I will talk about screen printed electrodes a lot. I will make that comment again. I'm perfectly aware that you've got the Welsh Print Centre in Swansea, and you've also got, as I say, Professor Owen Guy also has screen printing technologies there as well. I'm just going to hold a screen printed electrode up to the camera. The reason being is at Zimmer and Peacock, we have this new style of potentiostat. This is this new style of potentiostat. I know the camera is going to be a small angle, so in fact, I might stop sharing for a second. So this is this new style of potentiostat, and it can take screen printed electrodes. I just click that in like that just now. Now we put our design rules online, so that means if somebody wants to design their own screen printed electrodes, but either with Owen, or they want to do it through the Welsh Print Centre, they can design their own screen printed electrode. We've put our design rules online so that actually if people design to those rules, they can actually fit this device. And so suddenly you're not left with a scientific paper where it says, well, I designed a new screen printed electrodes, here's the raw signal. You can actually then carry the story forward and say, I designed a screen printed electrode, I functionalized it, I used it, admittedly, with the Sensei or potentiostat from ZP. And by the way, I was then able to put it into the real world, and here's some kind of clinical data. So it helps take the technology forward a little bit. So I'll be making that point a lot this afternoon. I will talk about electrode customization pros and cons. So there'll be talk of science, talk of technology, and also talk of some of the things that are going wrong a little bit in exploitation of science, if I can put it that way. I'll talk about electronics this afternoon, and I'll talk about the ZP commercialization strategy. ZP is on a bit of a journey at the moment, and the journey is going to be a 10-year journey, because I realize that even if we start teaching electro-analytical sciences like to undergraduates today, they're not really the entrepreneurs of the future for the next 10 years, but at least that they have their undergraduates to do, they've got their PhDs to do, and then they've got to launch their businesses. So I do expect this to be a 10-year journey, but we are very interested at ZP being involved in education, research, and commercialization. Just on commercialization, many of you know us, so I won't go on about it, but it may feel like we've been around forever, but in fact, this is now our 10th year. We started becoming heavily involved in Swansea probably about 7 years ago, or at least involved heavily. It's been much later on. We're ISO 13485. We do contract development, contract manufacturing. Just on the wearable biosensors, I'll go through wearables fairly quickly. But on wearables, in fact, ZP did do a master's program a few years ago with Swansea, and the student who did that master's program or master's project with us actually went on to work for Abbott. Now, the reason that is relevant to the camera, I'm holding this Abbott Freestyle Libre 2. So this is a CGM, a continuous glucose monitor. This is something that we've at ZP, we work on technologies like this. This is not ZP's technology, but what this is really is a representation of how powerful a science, electroanalytical science actually is. This is a wearable patch. It's got a battery, electronics. It's got wireless communication. It's got near field communication, I should say, strictly speaking. And the filament that actually sticks out of this device actually has an enzyme on it. So it's actually doing an enzymatic reaction. And it does the enzymatic reaction in the interstitial fluid and converts glucose, in this case, into hydroperoxide, and hydroperoxide is detected electrochemically. Something that Rajiv Shah does quite a lot of, and we do a lot of at ZP as well, is microneedles. There are quite a few papers out there from Swansea University about microneedles, both from Rajiv, but also from Owen Guy about microneedles for transdermal monitoring. It's probably worth saying that the watch that I have, this watch, I mean, it looks pretty nondescript, but it's actually got it's had 20 million euros invested in it. This patch is a microneedle patch, and this will go on my arm. And by doing the wrist strap up, it basically pulls the microneedles into my arm. So that's something that we've worked on at ZP. It's probably worth saying that we did try to do a KTP with the Welsh government and with Swansea University on this. It wasn't funded, which is a bit of a shame because the technology was quite mature and we were looking to make a bit of a partnership on that. Anyway, that said, at ZP we also work on non-invasive quite a bit, non-invasive monitoring in things like the sweat. We also work on implanted sensors. So implanted sensors would be interesting because at Swansea you do have I don't want to say an aquatic department, but you do have a department that works on fish farming and kind of coastal resources. And you have what's called a RAS system, a recirculating aquatic system. And a RAS system is something that we use at the ZP for actually doing fish studies, and I'll talk about that now. So this is an implantable biosensor from Zimmer Peacock. This is a great advert for electrochemical biosensing. This guy is only 15 millimeters wide and about 30 millimeters long. It does sound quite big when I tell you it's implanted. It's actually implanted into fish. So this fish is not dead. It's actually anesthetized. The veterinarian has essentially opened up the fish. The package is put into the fish, and the fish are basically sutured back together and put inside this recirculating system. So basically, there's a couple of salmon. This is post-operation, so they're actually swimming around at this point, having their glucose and their cortisol measured. As I say, this is at least the hardware. When I say the hardware, the ability to actually recirculate water like this in large volume is actually something that you do have at Swansea University. We haven't used it, but we have talked about actually doing some programs at Swansea on this. With that said, this is raw data that has been kind of basically streamed from fish as they swim around these tanks. What we're looking at here is a 9-hour period. In the first, so let's say half of this, the fish are just what we call baselining. They're not being particularly fed, but at this point they do get fed. And what we're looking at here is the raw electrochemical signal. It happens to be amperometry. And as the fish consumes the glucose or consumes the food, then their glucose signal goes up, signal comes up, and then it starts to sort of fall down over the next few hours. So that's an example, first of all, of electrochemistry. Then you could, underneath that term electrochemistry, it's really electro-analytical chemistry, and it's really an example of CGM, continuous glucose monitoring. But I would suggest in a really hard application, because actually that's done in fish whilst they're alive underwater, and you can appreciate the kind of robustness that takes. Something that we're pretty invested in at ZP is actually microneedles. So I mean, the reason that ZP in part exists is because electrochemistry was something that I want to say we accidentally fell into, but life is often like that. It's something that I became involved with when I went into industry. I've worked on a lot of these sort of sensors, and we work on a lot of electrochemical chemistry. Is one of those few sciences where you can take the analytical approach out of the lab and do it in the real world. And the glucose strip is a great example of that, because the glucose strip allows you to detect glucose in blood without any preparation of the blood. So many analytical systems require filtration, separation, centrifugation, maybe chromatography, and then analysis. Whereas electrochemistry, it can actually work on quite dirty samples, including blood. And then it's proven itself to be very robust, because actually you can translate exactly the same science actually into CGM, continuous glucose monitoring. So even though the blood glucose strip and the CGM patch look very different in terms of form factor, they're very similar science. And I think electrochemistry also, I mean, I'm holding up two devices now. The electronics in here are essentially both for the same. One of them, they're both running amperometric experiments. And amperometry is something that is come on this new potentiostat. So I'm giving you a kind of background that when I'm talking about teaching, researching, and translating, and I will use terms like cyclovoltammetry and amperometry, these are billion-dollar, let's say, technologies, because you can just look at the blood glucose space and understand that alone. For example, Abbott who make one of the leading CGMs. They've got a revenue of $55 billion per year, and I think about 10% of it comes from glucose. Dexcom, who make a CGM, a continuous glucose monitor, that is, they've just had their first quarter of 1 billion. So for the first time in their history, they have been around for 20 odd years at this point, but they just made 1 billion in the last quarter. So these are not insignificant businesses, and these are things is a bit of a term, but these are things that we should be interested in because A, they help people, and B, they make revenues, and the government does like revenue. So as I say, at ZP, we're very interested in microneedles, and we're also part of this CGM, this continuous glucose monitoring technology space. We do actually at this point have 50 patents on microneedles. 50 patents on, so this watch that I'm wearing is, as I said, I mentioned, had 20 million euros invested in it. Some of that, and you can appreciate how expensive this is, there's 50 patents on this technology, and ZP owns those. So obviously we're keen to exploit that, and that's something that we're working on at the moment. Well, I'm just mentioning microneedles to you. I know I'm off on a slight tangent here, and I'll try and bring myself back in a minute. There's a company down in San Diego, California, called BioLink. They probably have a similar sized patent portfolio to ZP. At this moment in time, in the last 4 years, they've raised 158 million US dollars. They haven't raised anywhere near enough to actually finish the job, but they have raised 158 million US dollars. So CGM, continuous glucose monitoring, a very good space to be in. And at ZP, we do sell technologies through our web store involved in CGM, both microneedles and also electronics as well. And we're also doing what's called a wearable potentiostat. So what I am showing in my hand at this moment is what I call an IVD, or point of need type device, where you have disposable sensors, you make a reading, you put a sample on the sensor, you get a response, you'll get a concentration on your phone, for example. That I would just call as a point of need or point of care diagnostic. When I'm talking about CGM, continuous glucose monitoring, that is where you're obviously constantly monitoring something, and in the case of CGM, it's glucose. And it's just to say that we do have a wearable potentiostat coming soon that can also be used in CGM. I will talk about the Sensei All platform this afternoon, slightly arrogantly named Sensei All, but I will talk about how I see that fitting into education and research, and also impact or translation of research into products. Something I want to talk about is just screen printed electrodes. So at ZP, screen printed electrodes are something that have proven themselves to be a successful technology. Successful in terms of, there are billions of glucose measurements made every year by, unfortunately, type 1 and type 2 diabetics, and a lot of those glucose monitoring is done on screen printed glucose strips. But it's not just glucose. There's a kind of company, for example, in Denmark, which called Radiometer, and they do a blood gas analyzer. And they're similarly actually using, and I've read their patent, so I know it's the case, they're also using thick film printing, i.e. screen printing, to make arrays of sensors, so that they can do CO2, oxygen, lactate, sodium, potassium, glucose, pH, I want to say, etc., probably some of the proteins as well. But they're doing all of this using electrochemistry on thick film printed / screen printed electrodes. So when I talk about technology and and undergraduate teaching and research and translation, I'm obviously promoting technology that I think, already has proven rather to be translatable. And if somebody says, well, what evidence do you have? Look at every glucose strip there is out there, and there are plenty of more complex instruments like blood gas analyzers using electrochemistry and thick film printing as well. Just as a side note, this is something that I do like to sort of teach, is when you're developing technologies, we're very focused on the kind of the science and the engineering performance. But when you're talking about translation, what makes a technology successful on the market is not necessarily what you first thought of. These are blood glucose strips. They were made by Johnson & Johnson, and they were the best-selling glucose strips on the market for a few years. And I got this straight from the product manager who worked on this product. And he said to, and he said, why do you think it was the best selling product on the market? And, you would immediately think, if I asked you, you say, or, precision, accuracy, sample size, speed. And yeah, these things are all important, but actually what made this the best selling product on the market was actually the fact that you could get it in different colors, pink, blue, and obviously silver here. And this came out just about the time there was a Nokia phone that everyone could change the cases on these Nokia phones. I know this is this is quite some years ago now, but it's sometimes what makes something successful and translate commercially is not necessarily something that we've been thinking about when we're doing the science and research. But just being able to change the color made that the best selling product on the market for a few years. I'm going to go back to screen printed electrodes now. So I'm going to spend some time talking about, I think the quality of screen printed electrodes is holding back research. Now, I know some of you might think, well, I don't care, I don't do this kind of research. But what we're finding is that, and I'm biased, so I have to kind of say, I'm not without bias, because actually, we manufacture these screen printed electrodes, but we try to manufacture them at a really high quality. But let's talk about screen printed electrodes first of all. Is the problem I see. People expect a low price on screen printed electrodes. Now, the reason I expect a low price on screen printed electrodes is because actually, if you look at the glucose strip, a glucose strip is quite a complex system, both in its its manufacture, its construction. It's got enzymes on it, and actually this glucose strip, which is made probably by thick film printing, or at least part thick film printing, costs 50 cents each, or 50p each. So people have an intrinsic expectation that screen printed electrodes are low price. But what's happening is people expect low price and they would like high quality. But in fact, what's happening is they'll get a low price and also get low quality. And what's happening is there's more choice than demand on that market. And I will talk about that in a minute. And there's also an oversupply and customization. I will talk about that as well. So the problem with SPs, the problem with screen printed electrodes, some of you, I know at Swansea, there's a big emphasis, there's kind of two technologies that are often used in the sensing, at least the electronic type of sensor I'm interested in. There's GFETs, graphing field effect transistors, and you are using a lot of screen printed electrodes as well. So let me just talk about the problem I see, at least on the screen printed electrode side of things. Just as a comment, the one thing at Zimmer Picot, we do sponsor a PhD at this moment who's using GFETs for gas analysis. When it comes to gas analysis, I actually think GFETs are really good technology. If I'm doing liquid phase work, I actually think that screen printed electrodes are a good technology. But we did try using them in a gas sensing program recently, and they weren't that successful. But the GFET is proving to be successful. So I just want to put that caveat in there. Back to screen printed electrodes. If you think about quality and price, if you're in the military, you need your technology. This is in general, it's not about screen printed electrode. You need your technology to be pretty good, because it's got to be, if it's body armor, you need it to stop, unfortunately, stop a bullet, for example. So you're willing to pay so you want quality, and they're also willing to pay price. Now, when you look at research, at least scientific research, is often very quantitative, and so we also want quality because we want to measure something. But because of the funding, it's not the same as the military. You can't. People don't have the budgets to have the same price, but they do want quality, and they do want, but they want that quality essentially at a lower price. So what is happening is people have a need, especially from the academic perspective, of, if I want an electrode, I want it at a low price, but I actually need high quality because I need to be able to produce graphs with it, show that I have a signal or concentration, or signal versus concentration. And for that, you need reproducible electrodes. Now, the problem is that we face is that if you want high quality and low price, and I think, if you're looking for high or a good product at a low price, I think if I hold up my phone, you can find phones like this for £250 and less. These are quite high quality at a low price, and how they get there is through high volume manufacturing. So I'm going to spend some minutes now talking about what's wrong with screen printed electrodes in general. Of course, I'm super biased. Unless they're ZP electrodes, you actually have a problem that you want high quality, you want them at a low price, but in fact you're getting low quality, and it's due to this problem of high volume manufacturing. If you want high quality, low price, you need high volume manufacturing. But let me break this down a little bit. So I can even think of a couple of printers in South Wales at the same time as well. So um, Zimmer and Peacock is one of many, many, many screen printing companies, let's say. So we are part of the problem. Hands up, Zimmer and Peacock, we are part of the problem of screen printed electrodes. There's many of us out there, let's say, and we come and go. You know, companies come in, companies that spun out of universities, companies go into liquidation. So there's a bit of a turnover in this market. And when you look at many manufacturers of screen printed electrodes, you'll find out that they've got a thick catalogue full of probably over 50 products. So lots of companies producing lots of products. And then you've got academia as well, you know, that are also producing screen printed electrodes. So in fact, you know, you've got commercial entities and academic entities all producing screen printed electrodes. What does this mean? If you can imagine that there were 10 people in the world, and we know there's a lot more than that, who are producing screen printed electrodes, and many of those companies are actually producing something like 50 or more different designs, and ZP is guilty of that. You know, this is where we started as well. You can imagine that 10 times 50 means that there are 500 products on the market. So it sounds great because actually you think, right, I'm going to do screen printed electrodes. I can find the lowest price because there's lots of vendors. I can find the design that I absolutely think I want because there's lots of choice. And in fact, I've got a choice of over 500 products. But then I would ask you a question. How many screen printed electrodes or electrochemical tests are done per year globally? You could think about your own lab. You could think about your colleagues. I would like to bet with you that across the globe, there's something like 1 million tests done per year on a screen printed electrode in the R&D setting. So in academia, from Joseph Wang at UCSD to Owen Guy at Swansea, to John Cooper up in Glasgow, all these different people, there's possibly something like 1 million at most tests being done on things like screen printed electrodes per annum. So there's only a finite demand for this. So 1 million screen printed electrode experiments. But in fact, if you think that those 1 million experiments are evenly distributed over those 500 products, that would suggest that, in fact, you only needed 2,000 of each one of those screen printed electrodes per annum. Now, I'll just hold up a sheet for you for a second. This sheet has something like 300 screen printed electrodes on it. So that means I could, if my back of the envelope calculations were correct, and I appreciate I could be making some gross errors here, but if I'm sort of correct, you could produce the global demand for screen printed electrodes in 7 sheets alone. Now, some of you will have been to the Welsh Print Centre, so you'll actually have a good sense of this. You can't manufacture screen printed electrodes in such low volumes, in fact. So the capability of producing screen printed electrodes is much more in excess of actually what's really required. So what's happening is people are producing quite large batches of screen printed electrodes. There's nowhere near enough demand for these screen printed electrodes. These screen printed electrodes are basically just going on the shelf and essentially aging. And we basically have a problem of over demand. So it's now what it is that you do want high quality and you want it at a low price. But in fact, when you look at the manufacturing volumes of, let's say, 7 sheets per annum, that's not high volume manufacturing. That's not even low volume manufacturing. It's almost like nothing manufacturing. So we've got a problem actually, which is too many vendors. We're one of them, offering too much choice. And therefore that all that choice is actually ending up diluting the very finite requirement for screen printed electrodes. So ZP, we're really trying to shift this because I think that actually there's a poor quality is generally coming out. It's offered at a low price. Now we do want to offer at the same price, which we are doing, but we're offering up a better quality. And this quality, by the way, makes it easier, both in educational terms, research terms, and translational terms. And the quality that I'm going to talk about is our manufacturing reproducibility, and I'll talk about that shortly. So at ZP, people come to us and say, I want all these, you know, I want certain designs, I want certain materials, I want, you know, a good price. And we're saying, okay, well, we do have actually a large catalog of choice, but we're actually going to suggest to you very strongly that if you want a carbon electrode, just take the 501. Why? Because actually we produce it in high volume. So even though I've got all sorts of designs and all sorts of materials, I say to people, please take this one. It's the lowest price I've got. It's the best quality I've got. And I think we're the only people really carrying that message. It's the same for platinum as well. We don't say, strictly speaking, ZP probably has at least 27 designs of platinum electrodes. But how many of them do we really sell? These days, we actually make sure that we're only selling 2 of them. So we're bringing everyone down onto the same electrodes, because otherwise we're doing what everyone else does, which is allowing all this choice. And all this choice means that nothing is manufactured in high volume. Because nothing is manufactured in high volume, nothing has the high quality that your other areas require. And I'm going to show you the quality part in a bit. And that then actually means that we're more efficient in when I say we, I mean ZP, we're more efficient in our development programs, because actually the underlying electrodes that we use are so good. And it also translates into a good experience in teaching, research, and education. So on price, we're making something at €1.76, which is probably £1.50. And on these ones, we're doing them about 90 cents, which is 90 cents euros, which is coming down to about 84p. Now, the quality is this. See that I'm going to jump slightly into back into my world of electrochemistry now, but people are using the wrong metrics when they're thinking about screen printed electrodes. I have had people tell me, well, what's your peak to peak separation in your cyclovoltammetry? Because I know why they asked the question, because they know that a perfect electrode, or a perfect system, I should say, would have a peak-to-peak separation of 59 millivolts. But if you're teaching, researching, and translating, getting close to 59 millivolts is good enough. You do not need 59 millivolts. It's the wrong specification when thinking about screen printed electrodes. The reason you're using screen printed electrodes is because you're imagining that you're going to make somebody a low-cost test. So is it more important to think about peak-to-peak separation when thinking about a low-cost test, or is it more important to think about reproducibility of manufacturing when thinking about a low-cost test? And I would definitely tell you it's more important to think about reproducibility of electrode when thinking about a manufactured product, and it's not peak-to-peak separation. So even though at ZP we can meet or come close to people's expectation on peak-to-peak separation, it's not the metric that you should be focusing upon. And I'll go a little bit faster now. So I've made a bit of a sort of thing about screen printed electrodes, but if you come to one of our demonstrations, and maybe we'll end up doing one, hopefully something in Swansea in October or November, there is some discussion that we'll be doing a workshop. You'll notice that we don't do any calibration when we're doing our product. Why? Because the underlying screen printed electrodes are so reproducible. What does that mean? It means simpler assays. You'll see us put samples on sensors, get a result. Now, often when you actually look at academic assays, there'll be some sort of normalization of data or some sort of pre-calibration. And we don't do all of that because actually the underlying electrodes are so repeatable. So repeatable electrodes mean no calibration. That means simpler assays, because everyone says, oh, I want to make a low cost assay. Well, simplicity is one of the things you therefore need to achieve if you want to make a low cost assay. So simpler assays are easier to commercialize. Easier to commercialize means impact. And all this really stems from this reproducibility of screen printed electrodes. So it's not by accident. We produce in high volume. In fact, we're now producing thousands a week of particular designs. So if you come to us and say, I want a low cost carbon electrode, I will say, you got 1 or 2 choices. Oh, I want this, I want that. No, don't do it, because you're going to end up with poor quality. We do testing like crazy to make sure that we stay there. So we'll take sheets like this. You can appreciate when I say like this, I'm just reaching down and grabbing one. We'll take it, we'll sacrifice electrodes from the sheet. We'll test them by cyclovoltammetry and make sure they're repeatable. This is also very important for teaching as well. Otherwise, you're trying to teach somebody something in the lab and you're trying to tell them that the peak height in your voltammetry is proportional to concentration. And they say, oh, but sir, but madam, this was more concentrated than this, but the signal is actually the wrong way round. And it's actually because the underlying screen printed electrode was irreproducible. So we make sure that actually the batches that we're shipping are really good. And we've had some gold electrodes in an undergraduate project this year. And I did get a little bit of feedback from the student. The student did a year out with us, by the way. So he did a year out with us. When he came back, I made sure we got some of our screen printed electrodes into his project, and he gives me some feedback that they're actually good. I was disappointed because he's also using some of our competitors as well, but There you go, c'est la vie. So these screen printed electrodes have made their way into Swansea, and there's also a new spin out coming out of Swansea that's also buying some of our screen printed electrodes as well. So I think the real metric when it comes to screen printed electrodes is not peak-to-peak separation. It's actually about reproducibility, and reproducibility for us is relative standard deviation. If we test a bunch of electrodes, what's the difference in their performance? And we're looking for better than double-digit performance. So relative standard deviation, for example, is 6. It's 5%. These are different sheets, but in the same run. So we're checking the signal, and we're making sure that the signals across a sheet are not all dramatically different. So we're doing that kind of quality checking before these things ever come out. So here I can see that our relative signal, for example, is 5.86 microamps, and our relative standard deviation was less than 6%. So then when we are testing at different concentrations, each color here represents a different concentration. The peak height in this case is proportional to concentration, and our error bars are small. I think it happens a lot in academia. In fact, people are actually they gather they're trying to make a calibration curve, and they're always getting outliers, and they say, well, it's probably a bad sensor, and they toss the data, and it's okay to do that as long as you believe it's the sensor. But it happens so much, but it very rarely happens with us, in fact, because why? Because we're making a reproducible electrode. So most of the signal is dictated by the concentration of the analyte, and we're not getting this noise on top of our signal due to the difference in area, for example, of the screen printed electrode. Again, you have to be very cautious with my statements, because obviously I would also be biased as well. Just be careful if you are using screen printed electrodes from us or from anyone. You've got to have good connection to them, otherwise they can look rubbish. So we do make sure that people get our connectors as well. I'll skip forward a little bit quicker. Customization is something that people do ask ZP a lot for. Can you make me a custom electrode? The quick answer is that people have an expectation with custom electrodes, and the expectation that they have is, I would like it at a low cost, but actually my company or my lab doesn't need more than 2,000 per year, so that's actually a low volume. Low cost times low volume equals low quality. That's the thing that people are not telling you. Low quality could show up in the idea of actually low yield. So this picture that I've got here is a company that went into liquidation. ZP ended up buying the assets of this company, but they went into liquidation because actually they went for a low cost, low volume provision of their screen printed electrodes, and they spent most of their time troubleshooting this low cost screen printed electrode. They actually had people just doing constant incoming quality control on these electrodes, and it ended up bankrupting the company. So they went into insolvency, which is good for ZP because we bought the assets, but it's not really the point, because it's a shame for the investors, it's a shame for the government as well. Just out of interest, at ZP, we do a lot of measurements on a lot of electrode materials, and I actually find out that geometry, for example, is not anywhere near as important as people think. If you're measuring small volumes on small electrodes with millimeter gaps, it doesn't really matter what the geometry actually is. So we've used rectangular electrodes, spiral electrodes, even parallel electrodes, where the electrodes are facing one another, and they all gave the same signal. So once upon a time, I would think, oh, electrogeometry must be very important, but actually, I now realize that because the currents are so small and the distances are relatively short, and the conductivity of many solutions is quite high relatively, it doesn't really matter about geometry anywhere as much as people want. Now, if I'm talking about research, where do you add the most value as a researcher? If you're doing biosensor development, whether it's on a GFET or it's on let's say, a printed electrode, where do you add the most value? You actually, and I've learned this in California, you actually add the most value when you do the assay itself. It's the assay where your intellectual most value add actually is. It's also in the method file. How are you going to get the best quality signal out of the assay that you've just developed? And then the last bit is the calibration. How are you going to extract information out of that assay? So in life, if you've got a choice, you've only got a certain amount of time. Time is your most important asset. You want to make an assay or a biosensor. Do you spend time on electronics and casing? No, actually, you spend time on the assay, the method, and the calibration. These three things, if you do these three things well, then you've invested well. These are the unknowns, the things that it's very hard for other people to do. But I'll talk about electronics. I mean, people put a lot of effort into electronics, but there are actually a lot of electronics out there. ZP is one of the manufacturers of electronics. You've got other, this is the potentiostat that I have in this office. I've got other potentiostats in this office as well, but electronics are something now that I would describe as becoming commoditized. So don't spend your time necessarily investing or building in electronics. The electronics that we have at ZP can do most of the analytical techniques that you would otherwise need for teaching, research, or translation of technology. At ZP, we do carry a lot of information about open source potentiostats, for example, on our website. But open source potentiostats, I think the real value in open source potentiostats is teaching teaching electronic engineers how to make electronics. The outcome that it's an open source potentiostat is not the value add. The value add is actually the person who's been trained, but it's not it's not the potentiostat itself. Something that we're very good at ZP is actually, I'm talking a lot about electrochemistry and a lot about screen printed electrodes, but this video that's playing in the top left-hand corner where one of our engineers is blowing into a device, this is something that we did. It's on the market today. What's called the legal owner of this is a company called Exhalation Technologies. Another one of the technologies that Solrun is running in the top right-hand corner is something actually I'll do a demonstration of in a minute. But at ZP, we're very used to putting this kind of technology into handheld devices, desktop devices, and even breath analysis systems. So they're all electrochemical. They're all using the same electronics. I just want to talk about the Valley of Death. When I came out of academia, it was quite a while ago now, there was always this Valley of Death. So the Valley of Death is this. This is you. You're in the lab. You're using instruments that don't look anything like products. You write scientific papers. Those scientific papers often bring you to technology readiness level number 3. The Welsh government and the UK government is very keen for you actually to get that technology out of your lab and into the real world. One of the problems is you're actually using, and I'm biased, but you're using instruments, and some of them I may have even provided, so I apologize for that. You're using instruments that are research instruments. So in my own biased way, I'm trying to give people instruments that look more like Apple type devices or Apple quality. These are consumer type products as R&D tools. So let's stop always using tools that look like they're scientific instruments. Let's start using tools that actually look like consumer products. So the Welsh government is very keen to close this gap between technology readiness level number 3 and technology readiness level number 9. It's not just the Welsh government as well. I'm also thinking about Innovate UK. There's a lot of Innovate UK grants, which are really about closing the gap, the valley of death between what you do in the lab and what can actually be done commercially. And one way of closing this gap at ZP is actually to physically close the gap. And what I mean by physically closing the gap is to start teaching people, both teaching and researching on tools that genuinely look and act like products that you could give to a clinician at Singleton or a doctor at Morrison. It's been too long. Stop using tools that necessarily just only can exist in the lab, and actually using tools that can exist in the lab and can translate out of the lab. So we're literally trying to close that gap between technology readiness level number 3 and technology ready level number 9. Now, when it comes to education, we are definitely trying to say, look, is it more inspiring, both when you're doing your research and when we're training undergraduates, to be using instruments that look like products? You don't have cabling, you don't have these strange slots that you have to slot these things into. They're small, they look modern. Is that more inspiring than necessarily using traditional R&D equipment? So I'm even thinking about when you're trying to inspire people today, is it more inspiring to be using technology that's actually smartphone driven? Because in fact, we live our lives on our smartphones, and these smartphones these days are so good they can actually drive the scientific equipment. And by the way, the app that I'm running, this app is available on the Google Play Store and on the Apple App Store. So this app is deployed. So if you've got a bunch of students, they all want to be teaching, they can just scan a QR code and they can install the app. The app automatically talks to the clouds, and I'll give you a demonstration of that shortly. So we do have a technology, it's called Sense It All. This QR code, I'll send you a recording later on. This QR code will demonstrate to you that it's actually on, you can scan this QR code off your Android phone, it will show you it's on the Play Store. You can scan this QR code off your iPhone, it will show you it's on the App Store. And we're just trying to basically get technology out there that's relevant, up to date, and is practical, that you can actually use it in a lab. And we feel like, and I'm biased, that these potentiostats are actually more inspiring, let's say, than we typically give people in their teaching. So we don't want the scenario where people are using necessarily large, bulky glass reactors, because that sort of makes people think, oh, that must be the state of the art, when the state of the art is actually solid state printed devices. The state of the art must be these large potentiostats upon which I can fit my potentiostat. No, state of the art is a small instrument like this. Even the laptop is now outdated. We can replace that with people's smartphones. A few years ago, people say, "Oh, what happens if somebody doesn't have a smartphone?" Well, nowadays, I'm sorry, go and find somebody go and find somebody under the age of 25 who doesn't have a smartphone. It'd be quite, well, apart from children, of course, but 18 to 25-year-olds are all carrying smartphones. So what we're trying to give is modern, relevant, and certainly up to date, and is already cloud ready. And we can do all of these normal techniques that you would otherwise do in a lab, but we can now do it on our smartphone, and we can go after lots and lots of analytes by doing this. I'm going to just say one final thing. The business model of Zimmer and Peacock is actually to provide tools for other people to be commercially successful with. So this QR code here, if you scan this later on, you're going to find out that, in fact, every element in this app is actually editable and replaceable. What does that mean? It means that if this app needs to say Swansea University or your spin-outs, your new co-company, it can all change, because in the end, it's a bit like, you're digging for goals, but ZP wants to make, if can I put it this way, ZP wants to make the shovels, let's say. I'm just going to check a quick comment that I got here. All right, that's cool. All right, thank you for letting me know you're going, but no props. So commercialization is something that we've got intrinsically built in. I'm going to go a bit faster now. We are trying to put these potentiostats actually into the teaching of undergraduate courses. So if any of you are involved in that, if you can lobby for us, I'd be delighted, because you can also borrow these potentiostats and put them into your research as well. But we are trying to put, tens of potentiostats into the teaching, thousands of screen printed electrodes, and all the cloud connectivity and all the reagents and all the protocols, so that people can just teach this stuff quite readily. I'm going to skip over a lot of this, but it just kind of says, look, this is one system which can, by scanning different QR codes and by using different electrodes, or sensors rather, can go from analyte to analyte. It's the same technology stack every time, same meter, same app, same cloud system. It's the sensor and the QR codes that will be the variables. So that's where that word Sense It All comes from. I just want to quickly stop for a second. I'm going to stop that. I'm going to change my camera just really quick and give you a quick demonstration. So, all right, so let's do a quick bit of cyclovoltammetry. In fact, what I want to do is I want to just change the target. Yeah, so I just changed the target of my instrument by just doing a QR code. I'll take one of the famous ZP screen printed electrodes I say is really good. Let's say I'm in a teaching lab now, I'm in a research. You saw how quickly I just made electrical contact, by the way. That is such a pain for most new people in electrochemistry. Where's the working electrode cable? Where's the counter electrode cable? Where's the reference electrode cable? Another beauty about electrochemistry, especially as a sort of field ready analytical technology, is I only just put 50 microliters on that particular sensor. I'm just going to send this data to I'm just going to first of all give my test the name, test. Yeah, that'll do. And I'm going to run assay and start measurement. Because I'm running one of our commercial assays at the moment, I did mention something about user experience. So the user experience here is, I am actually running cyclovoltammetry, but I didn't want to show them cyclovoltammetry because the user group who would use this particular assay doesn't care about cyclovoltammetry. But I will show you that, in fact, the cyclophotometry isn't lost to us. It's actually going to be saved up in the cloud. So it's just coming to the end here now. I just want to show you that, in fact, my finger is, there's an LED here that's actually flashing and changing colors. At the moment it says green, so it means that everything's kind of gone up to the cloud. So every time we do a test, I'm going to very quickly share my screen. I'm just logging into the cloud now. Every time hopefully I'm sharing now. Yeah. Every time I do a test, the data has gone up to the cloud. So it's not lost from you. In fact, you have all your data. So let's say you were, let's say you were working on an assay and you had some NHS collaborations going on, and the NHS contact you and they say, well, we're not getting sensible results. It's not working. Not working, for example, if I just did here, this would be a classic, that's not working. It's not working because I didn't put a sample on the sensor, but all those silly things that when you're trying to do translation or impact of science, people will do things that you don't otherwise expect. And it's very hard for you to troubleshoot. You might even have to go on a visit there. But of course, if all the data is going to the cloud, the way the system works is you can access that data. I can't, by the way, you can. It's your username and your password. You can access the data and you can actually go up there and troubleshoot. So we can look at sensible data, for example. And even here, see, this is my point earlier on, that this is cyclophotometry. Apart from people like Owen Guy and a lot of his group, for example, and Rajiv Shah. Nobody really likes to look at this kind of data. But in fact, you can see that we've trained the cloud to find the peak height, and turn it into micromoles. And that micromoles gets sent back to the phone, by the way. So it shows you that gap between lab experiments, so I would describe as raw signals TRL3, to something that would then go back to the phone, which is much more usable, like TRL7. This cloud will do. You didn't have to code it. You would come in, you would be able to predetermine what happened to the data. You can filter it. You can show extracted values. You can find the peak height. You can set windows. You can put formulas up here. So when I was saying earlier on, you need to develop that assay. You need to find the method file that you're going to use, and you need to know the calibration that you're going to use. For example, the calibration, we've put it up here so that we can turn peak height, in this case, back into concentration. So I think I'm getting pretty close to the end. So if I was to summarize up, microneedles are very strong at Swansea University. I'm glad that CISM now is coming online, because actually you have the capability of making some nice silicone type microneedles at the facility there. You do have the Welsh Print Centre. They've been running since the early 90s, I think. You've also got Owen Guy with his screen printing technologies as well. So if you're interested in printing your own electrodes, it does not exclude you from this platform. The design rules are online, or reach out to me and many of you will know it. I'm going to send you all an email anyway after this. And if we're very much hoping that you will, I'm biased, but start adopting the technology, because then it will get you from TRL3 to TRL9 much easier. It'd be great, just out of interest, the teaching of electro-analytical sciences in undergraduates is actually very, very rare in the UK. Even though this is a $1 billion industry, it's not taught. Electrochemistry is actually taught for fuel cells, batteries, capacitors, but not as an analytical science. So there's a bit of a gap, I could say, in the market there as well. So if you've got any questions, please don't hesitate to contact us. I do appreciate you all giving me, as again, your most valuable asset, which is your time this afternoon. It's come up to 3 o'clock, so I'm going to go and do the school run. So I am going to run off myself, but otherwise I will speak to some of you. I know I've got a meeting set up with you in the next week or so, but you'll get an email this evening, and if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much. Take care. Bye-bye.